Hello students, and welcome to section 2.3, Real Zeros of Polynomial Functions. In our beginning portion here, we're going to be reviewing long division of polynomials. I don't want to belabor this point. I could have actually considered this to be a review. What I am going to do is walk you through possibly one of these and then kind of guide you as to how another one can be done, at least setting it up, and then you can finish it on your own. So if you're dividing two polynomials, and by the way, typically we try to only use long division if in fact you cannot factor, but also if in fact another choice, which we'll take a look at later as far as dividing, isn't readily available. And there's other aspects of why we may use long division. But let's go ahead and warm up, and we'll dig into all the nuances later again. So 3x squared plus 7x minus 7. I'm going to divide that by x plus 3. So here, as you can see, I've set up my long division where that's my dividend, and here is my divisor. So the first step is to ask yourselves, x times what? I know the answer is there in the quotient, but think, x times what is equal to 3x squared. Now I underlined it in blue just to highlight that you're trying to find this first term in the quotient. It turns out it is 3x. So of course, multiplying 3x times x, I wrote underneath here 3x squared. 3x times 3, I wrote underneath here 9x. Now I did put it also in parentheses, and I'm going to be subtracting that minus that. So 3x squared minus 3x squared, as I anticipated, should in fact be 0. 7x minus 9x is negative 2x. Careful with distributing that negative, or at least considering 7 minus 9 instead of 7 plus 9. Be careful. So negative 2x. Now we consider again the same process, but now x times what, and I know the answer is there, but times what is negative 2x? Well, of course it's negative 2. So negative 2 times x, write it underneath. There you have it, negative 2x. And negative 2 times 3, there you have it, negative 6. Negative 2 minus a negative 2 is a positive 2. In other words, negative 2 plus a positive 2 ends up there being 0 as expected. And negative 2 times 3 is negative 6. We take negative 7 minus negative 6, or plus a positive 6, yielding negative 1. We can't divide into this value or this into that any longer. So really that ends up then being our numerator in our remainder. Okay, so this full answer, 3x minus 2 plus negative 1 over, and if you're wondering where x plus 3 came from, well, that was the original divisor. So this entire quantity is in fact your full-fledged final answer. So I would like you to try number 2 on your own. See if when you do it on your own you can model it to obviously take shape as this final answer. Be careful. This dividend is missing two terms. It's missing an x cubed, so you're going to fill in, kind of like a placeholder, you're going to fill in 0x cubed, and it's also missing an x, so I filled in, as you can see, 0x. When you go through and again ask yourself x squared times what is x to the fourth, you'll do the same basic steps. Obviously with this having two more terms, or one more term, excuse me, is a total of 3. You're going to have to multiply more than just once. You're going to have to also obviously multiply twice and then a third time to get this remaining quantity. Make sure you put it in parentheses yet again and subtract. What you're also going to need to do is you're going to have to drop these terms down. I don't know if I alluded to it technically back here, and I apologize, but I did actually bring down the negative 7 from up here. Okay, I didn't have to do that in the prior term, but negative 7 came down, and that's how I was able to subtract. And on this problem, you'll have to bring this term down and that term down as you see the process kind of continue. So go ahead and try that out on your own. The next page, yet again, is a review. Now, synthetic division technically is something that will most certainly supersede, so to speak, or take over if in fact you're asked to do it, or you have the choice between the two. In some cases long division is necessary, but once you guys get the hang of synthetic division, long division is obsolete, frankly, in most cases. So here's your dividend, here's your divisor. I took the divisor initially and I set it equal to 0. And the reason you set the divisor equal to 0 is because you have to perform synthetic division with this 0. Well, more specifically, let me take a step back. If your remainder is 0, then it is actually a 0. But in this case, because that may not actually be the case, and you'll see that it technically won't, let's just highlight it as x equals -2 to test the principle of possibly it being a 0, or frankly, if in fact we have a remainder that needs to be written as a fraction. Okay, so x equals -2, we test it in our little half box position here, and then we write the coefficients for. There is no x squared, so 0, -13, and then lastly 10. Notice the 0, because again I'm missing a term, has to take the place here. And then you finish off the following as you can see here. The very first thing when you do synthetic division is you add 0. So you're going to take 4 plus 0, and you end up, of course, with 4. Once you get that number, you're going to multiply it by that particular value, -2. So 4 times -2, of course, is -8. And then you just keep adding and multiplying, adding and multiplying. So 0 minus 8, that's -8, times -2, that's 16. -13, -8 times -2 is 16. -13 plus 16 is 3. Times -2 is -6. And then 10 minus 6, of course, 4. That is your remainder. If it did end up being 0, your technical value to start with was in fact a 0 of the function that we see here. We'll talk more about that down the road, but just as a heads up. Anyways, because we do have in fact 3 numbers here, with a 4th remaining as the remainder, like I said, technically it's partially part of the remainder. This is the first term. It's 4x squared, -8x, and then lastly 3. I know to write the terms in this manner because, well, this being the last term, it must be just a constant. This being the next degree up, so -8x, and then lastly 4x squared. This did come down, as you can tell here, as the numerator of this fraction. The x plus 2, yet again, came from the very beginning, of which we see here the divisor. Now, could I have done long division on this problem? The answer is yes. Do you really want to do long division now that you can see this process unfold? I would suggest probably not. Now, last year in Algebra 2, you probably did quite a bit of this. And when given the choice, I think this is pretty clear. Synthetic division trumps long division. Please take a look at number 2 on your own using similar processes. I would argue, though, be careful. Yet again, this second term here in the dividend is missing, so please fill it in as such with a 0. The answer is, in fact, very similar. Now, let's lead it into the next question. This leads nicely. We're going to go ahead and get rid of this. Okay. Because you are going to have a different assignment here. Anyways, I can delete that later. The remainder theorem. If a polynomial f of x is divided by x minus k, the remainder is r equals f of k. Use synthetic division to evaluate this quartic at x equals -2. So in a sense, it's similar to the last couple questions there, but you're already provided this value. The coefficients, as you see, are all laid out without any placeholders, so I don't have to fill 0 in for anything. And then I went through and I did the appropriate math. Add 0 first, multiply, add, multiply, add, multiply, add, and so on. You're finishing here with -100. You could consider this as part of the quotient, and therefore this would be part of the remainder over x plus 2 as the full fraction there. However, this is not actually wanting a function as a final answer, or a quotient, in other words. It's asking you to evaluate. What it really, if you think about it, is asking for is you to plug in -2 here, 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 and here. This particular result kind of speaks to that, and technically speaking, -100 would be the y value if you were to plug in -2 into those respective x positions. So there you go. That is f of -2, as you see, equal to -100. Again, simply an ordered pair, -2, -100. Kind of neat. So synthetic division serves more than one purpose. The factor theorem is on the next page. We are still in review mode technically. a polynomial, this is the factor theorem. A polynomial, f of x, has a factor x minus k if and only if f of k equals 0. So problem 1, given f of negative 2 equals 0, find the remaining zeros of that cubic. Now, because you're given this as a 0, and look at how convenient, in fact, the y value is. So negative 2, comma 0, you're told is, in fact, a point, which obviously is a 0 as well. That's the definition. You can quickly refer to the idea that x plus 2 must be a factor. So that's actually half of the answer. Let's plug in negative 2 into our synthetic division process with these, 1, 2, negative 3, and negative 6 as our coefficients here. No placeholders of 0 necessary, so add, multiply, add, multiply, add, multiply, add. So our remainder, not surprisingly, is 0. Okay. The resulting coefficients of 1, 0, and negative 3. Negative 3 is a constant. 0 is, obviously multiplied to anything to give you nothing, so we don't even write a middle term in our quotient. But the first term, of course, being 1, we've got x squared. So x squared minus 3 equals 0. And I actually wrote it up here to show that x squared minus 3 would be actually the nice kind of resulting factor multiplied by x plus 2. So this particular factoring representation only addresses how the factored form looks. If I take it one step further, as you can see here, I can take x squared minus 3. Obviously, because it's equal to 0, it's something that you can solve. I added 3. I took the square root of both sides, and therefore x equals plus or minus the square root of 3 as your resulting zeros. One thing you can test later if you'd like, and we haven't done this yet today, but you could theoretically store negative 2 on your graphing calculator, type in the function, and you should end up with the appropriate remainder. If in fact it's 0, it's a nice quick way, without necessarily doing the full synthetic division, it's a nice quick way to see how it results. And in theory, you could also do that with root 3 and negative root 3. Technically, you could also do it where, not necessarily being done on the calculator, you could use root 3 or negative root 3 here. Later we'll talk about how you can continue that process to do a whole factoring analysis and solving for that matter. So here we go. This is the rational zero test. Still review. I'm not going to belabor reading through this, but there are two key features if you look at a polynomial of this form. Every rational zero of f has the following version or form just to denote. P over q. P is the factor of the constant term a sub 0, so take the factors of that and divide it by q, which are the factors of a sub n, the leading coefficient. So for this first example, it says list all possible rational zeros. Remember, a rational number is a number you can write as a fraction. Zeros, we know, of course, are where the graph will cross the x-axis, so something comma 0 essentially. Now that something comma 0, that something is a possible rational that we're striving for, but as you can see here, this very first problem, the degree is only 5. Now I say only, we're going to see a lot of possibilities unfold, but technically because the degree is only 5, theoretically at most only 5 of those could be solutions. And there could be possibly, of those 5, maybe some repeated values, and possibly also, well, a minimum of 1 could work on a fifth degree function. We're going to talk about all the nuances of how the possible rationals end up being actual rationals, but let's go ahead and do the math where a sub n is 3, a sub 0 is 4. P over q is represented as the factors of 4, so 1, 2, and 4, and plus or minus needs to be assessed or attributed to those as well, because we can also, of course, say not just 1 times 4, but we could also say negative 1 times negative 4 to yield obviously positive 4 as your last term. Same goes with 3. Here are your factors of 3, plus or minus 1 and plus or minus 3. All of these numbers, in other words, 1 over 1, 2 over 1, 4 over 1, 2 over 1, 2 over 3, 1 over 3, 4 over 3, all of those numbers written as fractions, okay, 1/3, 2/3, 4/3, okay, those are all important in the context of then finalizing all of your possible rationals. In total, if you go ahead and double check here, all 12 of those possible rationals are a result of dividing P by Q. We'll go ahead and continue this at a later time. Please check the notes and try to fill it in on your own later.